Welcome back to Chapter 4 of Principles of Mathematical Analysis. In the previous sections, we built up the theory of limits and continuity for functions between metric spaces. Now we combine continuity with one of the most powerful ideas from Chapter 2, namely compactness. The central discovery of this section is beautifully simple to state. A continuous function sends compact sets to compact sets. From this one fact, we will harvest a whole crop of classical results, including the theorem that a continuous function on a closed bounded interval attains its maximum and minimum, and the theorem that continuity automatically upgrades to uniform continuity on a compact domain. We will also see, through carefully chosen counterexamples, that compactness really is essential to all of these results. Let's begin. Here is our roadmap. We start with a small definition of what it means for a mapping into Euclidean space to be bounded. Then we prove the key theorem, that the continuous image of a compact set is compact. From it, we deduce that continuous functions on compact sets are bounded and attain their extreme values, and that continuous one-to-one maps from compact spaces have continuous inverses. Next, we introduce uniform continuity and show it is automatic on compact domains. Finally, we show by example that every one of these results can fail when compactness is dropped. So far, our picture of continuity has been a local one. To check continuity, we look at one point at a time and ask whether nearby inputs produce nearby outputs. This is powerful, but it is fundamentally a local statement. By itself, it tells us very little about how a function behaves across its whole domain. Next, let's bring in a global idea. Compactness, from Chapter 2, is the global ingredient we are missing. Recall that a set is compact if every open cover has a finite subcover. This is a kind of finiteness property that lets us pass from infinitely many local statements to a single uniform conclusion. When we feed a compact set through a continuous function, something remarkable happens. When continuity meets compactness, we get some of the most useful theorems in all of analysis. We will prove that a continuous real function on a compact set actually achieves its largest and smallest values. We will prove that a continuous one-to-one map from a compact space has a continuous inverse. And we will prove that continuity on a compact space is automatically uniform. Let's start with one small piece of vocabulary. Here is the definition. A mapping F from a set E into k-dimensional Euclidean space is called bounded if there is a single real number m, so that the length of f of x never exceeds m, no matter which point x we choose in E. Geometrically, the entire image of the function sits inside one ball of radius m, centered at the origin. This is a very mild-looking definition, but it is exactly the property that our next theorems will guarantee for free when the domain is compact. This is the engine of the entire section. It says that if you start with a compact metric space, x, and push it through a continuous map, f, the image, f, of x is again compact. In a single slogan, continuity preserves compactness. Almost everything else in this section is a corollary of this one statement. Notice the proof will work directly with the open cover definition of compactness, rather than with sequences, so it is valid in any metric space. Let's look at the strategy first. Before the details, here is the high-level plan. We must show that an arbitrary open cover of the image has a finite subcover. The trick is to move the problem back to X, where we already know compactness holds. We pull each open set in the cover back through F to get open subsets of X. Continuity is exactly what makes these preimages open. They cover X. So compactness of X gives a finite subcover. Then we push forward and recover finitely many original sets that cover the image. Pull back. Use compactness. Push forward. Let's carry it out. We begin the proof. Let the collection of sets V sub alpha be any open cover of the image F of X. The key tool is theorem 4.8 from the previous section, which characterizes continuity topologically. A map is continuous exactly when the preimage of every open set is open. So each preimage F inverse of V sub alpha is an open subset of X. Look at the picture. The left oval is the compact space X. The right oval is the image F of X, and the many overlapping blue disks on the right are the cover sets. There can be a great many of them, possibly infinitely many. The dashed arrow labeled F inverse pulls each cover set back to a blue region inside X, and continuity is exactly what guarantees those pulled back regions are open. Next, we check these preimages cover all of X. Every point of X maps into the image, and the sets V sub alpha cover the image, so the preimages cover X. Now we use the hypothesis that X is compact. By definition, the open cover of X by these preimages must contain a finite subcover. So there are finitely many indices, alpha 1 through alpha n, whose preimages already cover X. On the slide, we now keep only these finitely many chosen sets, the 4 big disks highlighted in orange, and they alone already blanket all of X. That is equation 12, and it is exactly what compactness buys us. We have reduced an infinite cover to a finite one. Now we push this finiteness forward to the image. Finally, we apply F to both sides of equation 12, using the general set fact that F of the preimage of a set is contained in that set. The image of X lands inside the union of the finitely many original sets V sub alpha 1 through V sub alpha n. On the slide, the orange highlight has moved to the right oval, pushing the finite collection forward with the F. Those finitely many original cover sets now blanket the image F of X. That is equation 13. So we started from an arbitrary open cover of the image and produced a finite subcover, which is exactly what compactness requires. The proof is complete. Let us pause on the set fact we just used and picture why equality can fail. On the left, the function is not onto. The blue oval is the domain X. The red oval is the target Y, and the dashed region inside Y is our set E, containing Y1, Y2, and Y3. The arrows show that X only reaches Y1 and Y2. Nothing maps to Y3, drawn in orange. So when we take the preimage of E and push it forward again, we recover only Y1 and Y2, a strict subset of E. That missed point Y3 is exactly why F of the preimage of E can be smaller than E. On the right, the function is not one-to-one. Now E lives inside the domain and contains only X1, but a second point, X2, sitting outside E and drawn in orange, maps to the same image, Y, as X1. So the image of E is just the single point, Y, and its preimage pulls back both X1 and X2. That extra point makes the preimage of the image of E strictly larger than E. In short, missing image points shrink one side, and shared image values grow the other. Here's our first corollary. If the domain is compact and the function maps into k-dimensional Euclidean space, then the image is closed and bounded, and in particular, the function is bounded in the sense of definition 4.19. The reasoning is a two-step chain. First, theorem 4.14 tells us the image is compact. Second, the Heine-Borel theorem from chapter 2, theorem 2.41, tells us that in Euclidean space, compact is the same as closed and bounded, so the image is closed and bounded for free. This is especially powerful when the function is real valued. This is the famous extreme value theorem in its general metric space form. Let f be a continuous real valued function on a compact space. Define capital M to be the supremum of the values of f and small m to be the infimum. The theorem says these are not merely unattainable bounds. There are actual points P and Q in the domain where the function equals capital M and small m. In other words, the function genuinely achieves its maximum at P and its minimum at Q. The supremum and infimum are not just approached, they are reached. Let me show what this looks like. Look at the picture. The blue segment along the bottom is the compact domain. Here a closed interval from A to B. The two filled dots at A and B, together with the dashed verticals running up to the curve, remind us that both endpoints are included since the interval is closed. The dark red curve is a continuous function over that domain. The orange dot at the top marks the highest the curve ever reaches. Its height is capital M, and it occurs at the input P. The other orange dot marks the lowest value, small m, occurring at the input Q, which here happens to sit at the right endpoint. The theorem guarantees both of these dots actually exist on the curve. Without compactness, the curve might approach a high value without ever touching it. Compactness is exactly what nails the dots down. The proof is short because all the heavy lifting was done earlier. By the previous theorem, the image of f is a closed and bounded set of real numbers. Now recall theorem 228 from chapter 2. A closed and bounded non-empty set of real numbers contains both its supremum and its infimum. Apply that here. The supremum capital M belongs to the image, and the infimum small m belongs to the image. But belonging to the image means being an actual output value of f. So there are points where f equals capital M and where f equals small m. That is exactly the claim. Our next corollary concerns inverses. Suppose f is continuous 1-to-1 and onto, mapping a compact space X onto a space Y. A 1-to-1 onto map has an inverse as a function, but in general, the inverse of a continuous map need not be continuous. This theorem says that when the domain is compact, that worry disappears. The inverse is automatically continuous. In topological language, a continuous bijection out of a compact space is a homeomorphism. This is an extremely handy fact. Let's see why it holds. We begin by theorem 4.8 applied to the inverse map. It is enough to show that f of v is open in Y whenever v is open in X. So fix an open set V. Its complement, written V complement, is closed in X. Now invoke theorem 2.35. A closed subset of a compact space is itself compact, so V complement is compact. Pushing it through F and using our main theorem 4.14, the image of V complement is a compact subset of Y. Next, we turn compactness into closedness. By theorem 2.34, every compact subset of a metric space is closed, so the image of V complement is a closed set in Y. Now we use that F is a bijection. Because F is one-to-one and onto, it sends complements to complements. The image of V is exactly the complement of the image of V complement. We just showed that ladder set is closed, and the complement of a closed set is open. Therefore, the image of V is open. Since V was an arbitrary open set, this proves the inverse is continuous, completing the proof. Now a new and stronger concept. A function is uniformly continuous on x if for every epsilon greater than 0, there is a delta greater than 0, so that whenever 2 points P and Q are within delta of each other, their images are within epsilon. The phrase to focus on is for all P and Q. A single delta must work simultaneously for every pair of nearby points across the entire space. Compare this with ordinary continuity, where delta is allowed to depend on the particular point you are sitting at. Here, delta depends on epsilon alone. To build intuition, let us first picture what this uniform behavior looks like. This picture captures the essence of uniform continuity. The dark red curve is our function. First, fix a tolerance epsilon. Uniform continuity promises a single width delta that works no matter where we stand. Think of a box whose width is 2 delta and whose height is 2 epsilon. The box on the left is centered on the curve at the point P. Notice the curve enters through the left edge and leaves through the right edge without ever crossing the top or the bottom. The box on the right has exactly the same width and the same height, just centered at a different point, Q. And once again, the curve stays neatly inside. The very same box simply slides along the graph and always fits. That is what makes the continuity uniform. One delta controls how much the function can vary everywhere at once, not merely near a single chosen point. If the curve had a steep spike somewhere, no single box width would contain it, and the function would fail to be uniformly continuous. Now let us sharpen the contrast with ordinary continuity. Let us lay the two notions side by side. Ordinary continuity is a local, pointwise property. At each point P, and for each epsilon, we are permitted to choose a delta tailored to that point. As we move to different points, the delta we need may shrink. There is also a subtle grammatical point. It makes no sense to ask whether a function is uniformly continuous at a single point, because uniformity is a statement about the whole set at once. Next, the uniform version. Uniform continuity demands a single delta that handles every point simultaneously. For a given epsilon, clearly uniform continuity is the stronger property. Any uniformly continuous function is continuous just by fixing a point. The converse, however, can fail in general. A classic example is the function that squares its input, taken on the whole real line. Out near large inputs, the graph grows steeper and steeper, so no single delta can keep the outputs within a fixed tolerance everywhere. The surprising and beautiful result, which we prove next, is that on a compact domain, this gap closes. Continuity and uniform continuity become one and the same. Here is the theorem. If X is compact and F is continuous on it, then F is automatically uniformly continuous. This is conceptually profound. Continuity is a local property, defined point by point. Uniform continuity is a global property of the whole space. Compactness is precisely the bridge that lets us promote the local property to the global one. This is not just elegant, it is genuinely useful later. since uniform continuity is exactly the ingredient we will need to prove that continuous functions on closed bounded intervals are integrable. The proof is a lovely covering argument, and we will see explicitly where the finiteness of the subcover is the crucial step. Here is the strategy. We are handed an epsilon and must conjure one delta good for the whole space. At each point P, continuity gives a local radius, which we name phi of P, within which F varies by less than half of epsilon. We then cover X by balls of half that radius, called J of P. These form an open cover, so by compactness, finitely many of them suffice. Our delta is 1/2 of the smallest of the finitely many radii facie at those chosen centers. Because it is a minimum of finitely many positive numbers, delta is positive. A triangle inequality then finishes the job. Let's do the steps. Fix epsilon greater than 0, because f is continuous at every point. At each point, we can find a positive radius, which we call phi of p, so that any q within phi of p of the point P has its image within half of epsilon of the image of P. That is the half epsilon on the right of equation 16. Notice, we deliberately use half of epsilon, not epsilon itself. This slack will let two such estimates combine cleanly later. So far, this is just continuity, used separately at every point. Next, we build a cover. For each point P, define J of P to be the open ball centered at P, but with radius 1/2 of phi of P, that is, half the radius from the previous step. Why half? We are leaving ourselves room to maneuver. Each point P certainly lies in its own ball, J of P. So as P ranges over the whole space, these balls cover X. They are open balls, so this is an open cover of X. Now the compactness of X comes into play. Because X is compact, the open cover by the half balls has a finite subcover, finitely many centers, P1 through Pn, whose balls already cover all of X. That is equation 18. Now define delta to be 1/2 of the minimum of the finitely many radii phi at these centers. This is the heart of the proof. The minimum of finitely many positive numbers is itself positive, so delta is genuinely greater than 0. Had we tried to take an infimum over infinitely many points, it could collapse to 0, and the argument would fail. Finiteness, coming from compactness, is exactly what saves us. Now, the triangle inequality. Finally, take any 2 points P and Q within delta of each other. Since the chosen balls cover X, the point P lies in some ball J of P sub m, so P is within half of phi of P sub em of that center. Then Q is within delta plus that half radius of the center, and since delta is at most half of phi of P sub m, the total is at most phi of P sub m. So both P and Q lie within the full radius phi of P sub m of the same center. Applying our half epsilon estimate to each and adding, the distance between the images of P and Q is less than epsilon. One delta worked for every pair, so F is uniformly continuous. Having proved these theorems for compact sets, it is natural to ask whether compactness was really needed. This theorem answers emphatically, yes. Let E be any non-compact subset of the real line. Then part A says we can build a continuous function on E that is unbounded, breaking theorem 4.15. Part B says we can build a continuous bounded function with no maximum, breaking the extreme value theorem. And part C, when E is bounded, gives a continuous function that is not uniformly continuous, Breaking theorem 419. Let us construct these counterexamples. Suppose first that E is bounded but not compact. Then by Heine-Borel, it fails to be closed, so it has a limit point, call it x0, that does not belong to E. This missing point is the source of all our trouble. The first function on the slide, 1 over the quantity x minus x0, is continuous on E, since the denominator never vanishes there, but it blows up as x approaches the missing point, so it is unbounded. It also fails to be uniformly continuous near x0. The second function stays between 0 and 1 and is bounded, yet its supremum of 1 is approached only as x tends to x0, which is not in E, so the maximum is never attained. The picture shows why removing a single point wrecks boundedness. The dashed orange vertical line marks the missing limit point, x0, which is not in the domain E. The dark red curve is the function 1 over x minus x0. As inputs in E creep toward x0 from either side, the curve shoots off toward plus or minus infinity. Because x0 is a limit point of E, there really are points of E arbitrarily close to it, so the function takes arbitrarily large values. A continuous function on a compact set could never behave like this. The gap at x0 is exactly what compactness would forbid. Now suppose instead that E is unbounded. Then the identity function f of x equals x is continuous and clearly unbounded. Settling part A. For part B, the function x squared over 1 plus x squared is continuous and bounded, with supremum 1 that is approached as x grows but never reached, so it has no maximum. Finally, part C genuinely requires E to be bounded. If we drop that, the claim fails. Take E to be the set of all integers. Any two distinct integers are at least distance 1 apart, so choosing delta less than 1 makes the uniform continuity condition hold vacuously, and every function on the integers is uniformly continuous. Our last example shows compactness is also essential in theorem 4.17, the continuous inverse theorem. Let x be the half-open interval from 0 up to but not including 2 pi, and wrap it onto the unit circle by sending t to the point cosine t sine t. This map is continuous, 1 to 1, and onto the circle. The continuity and periodicity of sine and cosine will be established rigorously in Chapter 8, yet the inverse map fails to be continuous at the point 1, 0, the image of t equals 0. The reason is that the domain, the half-open interval, is not compact. Let me show the geometry. On the left is the domain, the half-open interval from 0 to 2 pi, with a solid dot at 0 included and an open dot at 2 pi excluded. On the right is the unit circle, the image. As t increases from 0, the point travels counterclockwise around the circle and returns toward the starting point 1, 0, marked in orange. Here is the trouble. Inputs just below 2, pi land very close to 1, 0 on the circle, and so does the input 0 itself. So nearby outputs on the circle can come from inputs near 2 pi and from inputs near 0, which are far apart in the domain. The inverse must therefore tear the circle open at the seam, and that tearing is exactly a discontinuity. Note the circle Y is compact, yet the inverse still fails, because it is the domain that must be compact. Let us gather everything together. The cornerstone of the section is theorem 4.14. A continuous function maps compact sets to compact sets. Continuity preserves compactness. every other result we proved flows from this single fact. Let's recall those consequences. From the cornerstone, we obtained the extreme value theorem, theorem 4.16. A continuous, real-valued function on a compact domain does not merely stay bounded. It actually achieves a largest value and a smallest value at genuine points of the domain. This is one of the most used theorems in analysis and optimization. Next, the inverse and uniform continuity results. Two more corollaries. Theorem 4.17 says a continuous one-to-one map from a compact space onto another space has a continuous inverse, so it is a homeomorphism. And Theorem 4.19 says continuity on a compact domain is automatically uniform continuity, with the finiteness of a subcover being the decisive ingredient. Finally, a word on why compactness was indispensable. And the counterexamples of Theorem 4.20 and Example 4.21 show the hypotheses cannot be weakened. On a non-compact set, we can find continuous functions that are unbounded, that have no maximum, or that are not uniformly continuous, and a continuous bijection whose inverse is discontinuous. Compactness is genuinely doing the work. In the next section, we pair continuity with the other great topological property, connectedness, and we will recover the intermediate value theorem. Thanks for watching, and see you there.